Good morning to the galaxy of young intellectuals. I, Shivani Kush, on behalf of the Office of Academic Outreach and New Initiatives at IIT Delhi, extends a very warm welcome to the distinguished faculty, teachers, management, and to my dear students. We are thrilled to host our 9th session of Sci-Tech Spins Lecture Series, an initiative of the Office of Academic Outreach at IIT Delhi, which aims at enriching the educational experience of high school students. It's my honor to welcome you all. It brings me immense joy to introduce you all to Professor Ayan Bhowmik, our eminent speaker of the day from the Department of Material Science and Engineering at IIT Delhi. Dr. Ayan Bhowmik completed his undergraduate studies in Metallurgical Engineering at Jadavpur University and his master's from IIT Bangalore. Then he went to do his PhD at the University of Cambridge, working on designing and developing refractory metal systems for jet turbine application. This was followed by professional experience at the University of Cambridge, Imperial College London, and Royal Ross Corporate Lab, Singapore. He then returned to India in 2009 to IIT Delhi, joined as assistant professors in material science and engineering. He has been since then leading a group on novel materials and advanced manufacturing technologies. Besides research, Dr. Bhowmik is highly passionate about teaching. Going beyond curriculum-based lectures, he continuously seeks new means and methods to make both his lectures engaging and create a lasting impression of complex engineering concepts. In today's talk, he is going to tell us about super strong materials that are designed to fly. Now I hand over the mic to Professor Ayan Bhowmik for his valuable words. Sir, please. Can we have a round of applause, please?
Good morning all. Am I audible? Am I clear and audible? Yeah. Thank you all very much for braving the fog and the cold winter to come all the way from different parts of Delhi to our campus in Haus Khas. It's great to see you all having a good time and all with smiles on your face. Yeah, mostly all smiles. So today I'll be talking about materials that are used in aeroplane engines, yeah, in jet engines. So they are the materials that make us fly, yeah. So let's start with an introduction. How long do you think the longest flight in the history of human civilization has lasted? The longest flight. Any guesses? I'm sure you must have done a lot of air travel. You must have been on flights numerous times. But what is the longest that you have experienced, and what do you think is the longest that has ever happened in human history? No, that's
17 to 18 hours.
17?
18 hours.
17 hours. Any more guesses? Huh? 19? 19? Did someone say 19? Yes? Yes? 19. Yes, you are very close indeed. So Qantas company, they had completed what they called as a double sunrise non-stop flight from London to Sydney, and it lasted for 19 hours and 19 minutes precisely, and covered a distance of 17,800 kilometers. So to put things into perspective, so 17,800 kilometers, suppose you are flying from Bombay to Delhi, how much would be the distance in kilometers roughly? The flight time will be 2 hours. So in terms of distance, it will be roughly how much? 1,500, 2,000 kilometers. So this is a whopping 17,800 kilometers from Sydney. You can imagine where Sydney is on the world map, and then flying all the way non-stop to London, during which time it saw 2 sunrises. So that's why the flight was called a double sunrise flight. Okay? So it happened under the Project Sunrise. But there have been other flights too, which have been operating between New York City and Singapore. You can imagine where their locations are on the world map. That flight lasts a non-stop of 18 hours and 50 minutes. Flight from Singapore to Newark, which is in New York, close to New York. That flight lasts for 18 hours and 45 minutes. So imagine a piece of aircraft flying at an altitude of 33,000 feet and going through and operating non-stop for 18 hours and 45 minutes. Yeah, 18 hours, 19 hours, 20 hours. So what makes them so special? It is actually the engines that sit under the wings that you see when you board a flight, especially not from the aero bridge, but if you board a flight from your bus, the bus takes you to the base of the flight and then you walk up the stairs. So you see that there will be these engines which will be tucked under the wings of the aircraft. Yeah, there can be 2 engines, there can be 4 engines. So most of the time it's 2 engines. But if you are going for a long haul flight, very long haul flight of the order of say 19 hours, 16 hours, 17 hours, whatever, you'll probably be flying with an aircraft with 4 engines in them. Yeah. And so to put things into perspective in terms of scale, how big does it look like in comparison to a full-sized human figure? So this is a human being standing, an average-sized man standing next to an engine, and you can see it's roughly double the height of this particular gentleman. Okay, and you already have a good appreciation of the scale of the engine when you stand next to it when you are boarding the aircraft. Yeah. So this is a jet engine. Yeah, and so this is looking through the jet engine cross section, but from a materials perspective. What we see that there are a lot of different materials, mainly alloys, that make up the engine architecture, okay? And amongst which are metals like aluminium, titanium, steel, nickel. So they are all color-coded, red being nickel, steel are the orange sections, titanium are the blue sections, and aluminium is the yellow sections. So can you guess roughly which material occupies the maximum proportion of metals in the how much? What? Who says titanium? Can I have a show of hands? Okay, fairly large number. And who thinks it's nickel? Okay, not as proportionate, but still. But I would say that it's actually nickel, although from the size it might be a little misleading from this figure. But nickel occupies approximately 40% of the entire material that is used in jet engines, whereas titanium occupies very close 30% of the total volume of metals that are used in such engines. Yeah. So without a shadow of doubt, nickel and titanium, they are the major workhorse material in a jet turbine engine. So, and if you can see that there are several sections in which a jet turbine is, or in which this engine is divided into. First comes the compressor stage, then comes the combustor stage, and then at the back of the engine is your turbine stage, okay? So these sections, they all have their distinct roles to play when the engine is under operation, okay? So now very quickly to glance you through what actually every section does. So the first part of the engine that you immediately see standing out of the aircraft is the large fan blades, yeah? Next time when you board a flight, just get in, try to appreciate the scale of the scale of the size of these fan blades as compared to your own height, okay? So these fan blades are made out of titanium, okay? So so the first section is the fan blade, and its job is to suck as much of air as it possibly can, okay, from the atmosphere. And then comes the compressor stage. So all these, I don't know if the laser pointer works, but yeah. So this section here, the next section of the fan blade, which is called the compressor section, and its job is to, as the name suggests, is to compress the atmospheric air into a small volume, okay? And this compression ratio is typically of the order of 40:1 or 50:1. So if I have a 40 liter of, so the fan blade will suck in 40 or 50 liters of air and will compress it into 1 liter. That's what I mean by compression ratio, okay? So that's the job of a compressor. So next stage is, so compressor squeezes the air volume. Next comes the combustor engine, where you can see it's written bang. That means it's combusted, it's burnt. Yeah, so there you have, in that section, you have the fuel injectors, from which the airplane fuel is injected, and then in presence of the and that burns your compressed air, okay? So there you have the bang operation happening in the combustor section. Then comes the turbine section, which job is to then blow out the very hot air, which has just been combusted, out from the back. So as the hot air is blown out from the back, that gives it a forward thrust, that gives a forward thrust to the engine, which makes the aircraft propel forwards. By which law of motion? By Newton's third law. Very good. Very good. So the whole operation of a jet engine can be summarized as suck, squeeze, bang, and blow. So can you repeat after me? Suck, squeeze, bang, and blow. Yeah? So now I have talked about the turbine section. So now you know where the turbine section sits within the entire engine architecture. So turbines are obviously, so if I'd ask you which is then the hottest part of the engine, the answer will be my turbine section, because that is the first section which sees the hot air that is being combusted in the combustor coming out from the back end of the engine. So the first few stages of turbine sees let me pull up the laser pointer. So this part, the first stage of the turbine section sees the very hot air that comes out straight from the combustor section after being burned. So, and within this section, you have numerous such turbine blades which run at a very high speed. Okay? Okay? There are numerous such blades which run at very high speed, and they're called the turbine blades. Okay? Can some of you guess what sort of temperatures would the turbine section experience? What sort of temperature? When the fuel is burnt, huh? 800 to 900? Not really. Anyone from the middle section? Huh? Somebody says 2000, 2500 from this section? Any numbers? 1000 degrees? No, the actual answer is about 1500 to 1700 degrees Celsius. So imagine 1500 to 1700 degrees Celsius, a part of your aircraft experiences while you are sitting cozily and comfortably inside your cabin, yeah, and complain about little things that my seat is taken by someone else and I am not having enough to eat and so on and so forth. The menu in Indigo is not so great, or in Air India is not so great. But imagine there are other things which are of more importance when you are traveling, when you are doing an air travel, yeah. So this section, where you are sitting nice and comfortable, this section of the engine is working continuously for the duration of your flight at a temperature of around 1500 degrees Celsius. So 1500 degrees Celsius. Your water boils at 100 degrees Celsius. Aluminium melts at 600 degrees Celsius. Steel melts at 1500 degrees Celsius. Steel melts at 1500 degrees Celsius. So that is the sort of temperature that is reached in these sections of the engine. And if you look at each of these turbine blades, they are tiny compared to the entire scale of the engine. So they are about 10 to 12 centimeter in height. So for a quick demonstration, I have got a turbine blade for you to see. Okay, so this is a turbine blade, actual turbine blade that goes and sits in one of the turbine sections. Okay, so maybe I can ask Nidhi to show some of the students around. You can get a feel of it. So imagine, so you can feel how heavy it is, and look at the intricate architecture, the engineering design that has gone into fabricating this turbine blade. Okay. Okay. So from the front to the back end of the engine, the entire jet engine experiences a temperature range of somewhere between minus 50 degrees, because that is the ambient temperature in your stratosphere, minus 50 degrees Celsius, to as high as about 2000 degrees Celsius. So that from the front to the back end, okay? The maximum the temperature that is reached in the turbine section of the engine is 1500 degrees Celsius. At which these blades, which are connected to large discs like here, which again are in turn connected to long shafts that run from the front to the end. And as it spins, the blades will also spin with the disc. Yeah. So the revolutions in this case is 10,000 RPM. 10,000 RPM, the engine performs, the turbine engine performs at 1500 degrees Celsius non-stop. Okay. And that is akin to having a load of, if you calculate the centrifugal force, the load will be 100 kilonewton, of the range of 100 kilonewton. Oh, you still have to play. Maybe you can show some of the students there on that side. Yeah. So do you have a feel of Newton? Do you have a feel of how big is 1 Newton? Because now we are talking about 100 kilonewton. 100 multiplied by 10 to the power 3 Newton. So do you have a feel of what a Newton is? Suppose if you punch someone or you get punched with a force of 1 Newton, how hard it will hit you. Not that I'm saying that you go around punching people, but do you have a feel of 1 Newton? Anyone? What is the force that you would experience if somebody punches you that is of 1 Newton? How hard it will hit you? Who says that? A teacher? Yeah, that's right. Okay. And anyone else? More practically speaking. 100 grams, then my question would be, what is 100 gram? Do you have a feel of 100 gram? You still have the blade, right? So 1 Newton, let me tell you, 1 Newton, as madam said, 100 gram, but what is 100 gram? You have to put that imprint in the child's mind. So what is 100 gram? Is holding an apple on the palm of your hand. Okay, the force that you experience is 1 Newton. Okay, maybe you can hold the apple and see for yourself. Okay, the apple weighs about 100 gram, a big apple 120 gram, but this is 100 gram. Okay, so holding an apple is your 1 Newton. And so this blade is experiencing at the tip a force of 100 kilonewton. All right? Thank you very much. Could have eaten it. I thought you would have eaten it. So this is what? And 1 Newton force is the force that is experienced by the hand while holding up an apple. And as I said, 100 kilonewton at the tip of every blade is like having a full body truck attached to the end of each blade. And see what happens to the blade. So the picture looks something like this. So as it rotates, it's like having a truck hung at the tip of each blade. Okay. So every truck is so 100 kilonewton is how many ton? Is 10 ton. So a full-size big truck would weigh close to 10 ton. Okay. So now, obviously, that brings questions to our mind, that casts questions in our mind, that what material should be used, as going by the title of my presentation, which materials should then be the most suitable for this sort of turbine blades. So the answer is nickel superalloys. Nickel superalloys. So nickel superalloys are a complex class of metallic alloys which comprises of a mix of around 10 different elements. Okay, so these are the bases of nickel, and on top of that, you sprinkle bits and pieces of other elements, for example, titanium, niobium, tantalum, hafnium, zirconium, molybdenum, aluminium, iron, cobalt, so on and so forth. Depending on what grade of material that you are using, you will use these elements very judiciously up to particular concentrations that you want. So it's much like, and you have to make sure that you choose your elements judiciously, and you also choose the amount that you add of the material very judiciously too. So otherwise, it will spoil the biryani that you would have liked to eat. Yeah, because when you cook a biryani, you have to know your ingredients, and not just the ingredients. You also have to know how much quantity of each ingredient should I be adding. So nickel superalloy, when you're preparing an alloy, you have to keep in mind. So you have to add these, or it has to be from this mix of elements, but to what extent, that depends on the final property that I would want to have from the alloy. Okay, so nickel superalloys. So this is like the Superman of different alloy systems that exist, metallic alloy systems that exist. So that's why they're called superalloys. It's stupid, right? They're Superman, superalloys. So what? So Superman says that they are as strong and tough like me, the superalloys. But what is the reason that they are called superalloys actually, scientifically? Is that if you now compare superalloys, nickel superalloys, with any mundane material, for example, your humble steel, and what I've got here is a plot showing yield strength on y-axis that is the strength of you can take yield strength as a strength of the material on y-axis, and temperature on your x-axis. So most of the metals, you would have learned from your high school physics or chemistry that metals and alloys, typically they lose their strength at high temperatures. So you'll see that the strength curve of steel gradually falling down with increasing temperature, which is as expected. Over here is the red section. The red section highlights the temperature at which the temperature that is experienced typically by the turbine section, various sections of the turbine engine. Okay, so, but for superalloys, you see the strength reduces, but only very gradually, very minimal amount. But then something happens near that window of operation, which is the red zone, that it sees a peak. Yeah, there is sudden jump in strength at operating temperatures of the turbine section. So that's why this is called superalloy. So their behavior is very different from that of steel. So in order to understand why this is the case, you have to come to IIT Delhi to study material science and engineering after passing your joint entrance advanced examination. So nickel superalloys, they retain their high strength at high temperature, and they have exceptional properties, and that is the reason why they are called superalloys, nickel superalloys. But you don't have to take my word for it. Yeah. So I have a demonstration planned for you all to see. Okay. So that superalloy is actually stronger compared to steel. Yeah. So for which I would invite my very obedient and very good student, Pranav, to come on stage. Can we have a round of applause for Pranav? Thank you. So okay, that's enough. Thank you. So what we have here is, so Pranav, Ajay, you can move on to the next slide here. So what we have here is two wires, one which is made out of superalloy and the other which is made out of steel. Okay, and then what we will be doing, Pranav will be handling the superalloy and I'll be handling the steel. And what we will do is that we would hang a same amount of weight to the tip of these wires. Okay, so that they have the same loading conditions. Okay, so the torque that is felt by each of the wire is the same. And then what we will do, as I said, that at high temperature, steel would easily bend, will give away because its strength reduces drastically as compared to nickel superalloy. So what we will do is that we will heat this wire, and you have to guess, well, no prizes for guesses. So which material or which wire would give away first? Okay? Yeah, ready? So what we will do is that we will light up the candle and then light up our torches. Okay. And you can see that Pranav is wearing, this is quite dangerous. That's why Pranav is all suited in PPE. He has got all the attire ready. He is wearing a lab coat. He is wearing gloves. He's also wearing his protective glasses. Yeah. So when you are working in lab, always make sure, or when you're doing scientific experiment, make sure that you follow the proper protocol of wearing the suitable PPEs. The lab coat does not fit me, but I have my glasses. I have my gloves, and we will soon be. So should we blow our torches up? Okay, ठीक है. We will stabilize. ठीक है? Okay. So ready? Start. Are we ready for the demo? So what we will do? There you go. It's already sagging, whereas this is still holding up. Yeah. So the steel, obviously, this does not work, whereas our superalloy still goes strong and strong and strong, yeah? Okay, are you convinced? Yeah? Okay. Thank you. You're done, Pranav. So let us thank Pranav again for his active participation. You're done, Pranav. So what actually lies inside these blades that makes them super strong? So what is the reason for their strength? Okay. So this is a 12 centimeter blade that I have already passed along and you have already felt by your own hand. So for this, we need a microscope, a special type of microscope, which is called the scanning electron microscope. Okay. Typically, for any microscope, for example, the optical microscopes that you must have used in your practical lectures, in your practical classes, they work on the principle of reflection of light. But in this case, we use an electron beam to raster the surface of a sample that you put inside the microscope. And because the resolution, because the wavelength of electron is much lower than the wavelength of light, you'll be able to resolve much finer features by use of an electron beam. So for this, we would stick our sample inside a scanning electron microscope to see what is the structure, what is the internal structure of these blades. So what we see is that, so initially, when the blades used to be manufactured, say 3 or 4 decades back, these blades would have a lot of these. Okay, so these blades firstly are made by casting. So who knows what casting is? So it's basically liquid to solid processing. Okay, so when you pour in liquid metal in your mold, it solidifies to become the final structure. So that is called casting. So these blades have been fabricated over generation by castings. But in the earlier generation, what used to happen is that after casting, within the blade, you would get such polycrystalline grain structure. So these grains, as you can see, are quite rounded. The different colors that you see these are individual grains, and they are quite rounded, and that's why they are also called equiax grains. Okay, and there are many grain boundaries. So, and if you zoom in, so that these are each individual grains, and then the black lines are the grain boundaries. Okay, then what happened that with advancement of technologies, these blades started to get manufactured with longitudinal grains, still by casting, but then instead of these equiax grains, we could see longitudinal grains, wherein we could get rid of the cross boundaries that were present, so that during loading, they won't fail from the cross boundaries. So this is like stitching up multiple pieces of cloth together along its length direction. Okay. So obviously, you could still argue that there are still boundaries which would make the material weak, yeah, because grain boundaries are your points of weaknesses in the material. So suppose if you have stitched cloth like this, the points of weaknesses definitely will be along the stitches, yeah. So it can still fail along the stitches or the grain boundaries in this case. So what eventually happened is that the most advanced blades of the modern times are now being made completely free of boundaries. Or in other words, they are made of a single crystal. There is one crystal which is there in this entire piece of blade. So there are no grain boundaries, but a single crystal of nickel superalloy. Okay. So they don't have these longitudinal grain boundaries. Neither do they have these equiax grain boundaries. Okay. If you look further deep inside the microscope into the structure of this single crystal, what you would see something like this. Okay, this is called the microstructure, because if you point your eyes to the scale bar, you would see that the scale bar is only of 1 micron. So what we are looking at is a section which is 5 micron by 5 micron. Okay. Again, to get an idea, a feel of the scale, how much is 1 micron? So how small is 1 micron? So what is the thickness of typical human hair? Thickness of typical human hair is 80 micron, 80 to 100 microns. Okay. 1 micron is 10 to the power minus 6 meters, 10 to the power minus 3 millimeter. So human hair, the diameter of human hair is typically 80 to 100 microns. And this we are talking about a section which is inside this single crystal blade, which is 5 micron by 5 micron across. Okay. So here, what you see, there are, and if you have, so that's why it's called a microstructure, micron base level structure, microstructure. And if you have an artistic imagination, you would see you can resemble this microstructure with the skyline of San Francisco, where the buildings would be these square blocks, and the roads will be these channels that run across horizontally and vertically. Okay, so something like that. So now let's look into what these micro components are. So this is one micro component, which is the brighter phase, and then you have the channel, the micro component, which are these channels. Yeah. So these micro components are also called phases of a material. Phases of a material. Okay. So that means there are two phases in this material. One, which are these cuboidal. They look square, but they are actually cuboidal. Yeah. In 3D, they are cuboids. So these bright cuboids and these channels. So these channels are typically your pure nickel. Okay, pure nickel with bits and pieces of some other elements dissolved in it. Yeah. So mostly nickel, and this is the structure of nickel, because you know that metals are all crystalline. What do you mean by crystalline? Crystalline means periodic arrangement of atoms. Yeah. So that periodic arrangement of atoms make a crystalline structure. So this is a periodic arrangement. Both of these phases are metallic phases. So they have periodic arrangement of your elements in 3D. So this is nickel, where all the sites are occupied by nickel atoms only. Whereas in this case, these phases, or the microcomponents as you want to call them, this phase is called Ni3L, nickel 3 aluminium. Okay, so that means this phase has 75% nickel and 25% aluminium. And this is how some particular sites within the crystal are taken up by red nickel atoms and blue aluminium atoms. Okay. Okay. So as I said, that the turbine entry temperature in a high pressure turbine is typically 1500 degrees Celsius, but the melting point of pure nickel is around 1455 degrees Celsius. That of nickel superalloys, which is an alloy of nickel, you all know that melting point of alloy is less than the melting point of pure metal. You all know that. So melting point of nickel superalloy, which is an alloy of nickel, is even lower, which is 1350 degrees Celsius compared to pure nickel. So don't you think that under this operating temperature of 1500 degrees, yeah, these blocks of turbine blades would melt? They should melt, right? Because melting point is far below than the operating temperature. So this should have gotten melted. Huh? You wouldn't have been able to fly with these. So then what? So there must be some sort of engineering modification, engineering design that must have gone into it, yeah, inside these blades in order to make them not melt or make them stay put even at high temperatures. So as I was passing the blades, I don't know if you have noticed, there are these intricate channels which are made into these blades, yeah. So they are there for a reason. So you can see that these channels are there even in the cross section of this blade that you just held in your hand. So these channels are actually for cooling. So you have cool air as the turbine is rotating, as the blades encounter 1500 degrees Celsius. There are channels inside the grains through which cool air is circulated. Okay, so that cool air helps to lower the temperature of the blade. Okay. There is another strategy that is applied by engineers while such blades are manufactured, is that of coating. So you can see that this is a cross section of the blade. Yeah, this is a cross section of the blade. The top part is. So sometimes what you do is that you can apply a ceramic coating on top of the metal. Okay, you know that ceramics are insulators compared to metals. So that means the temperature with the ceramic coating, the temperature that the surface of the blade sees, the metallic surface of the blade sees, is only 828 degrees Celsius. This is the inner temperature of the blade. Whereas if there had been no coating, then the top surface of the metal would have experienced a temperature of 1000 degrees Celsius, which is all very close to its melting point. Okay, but because you apply a layer of ceramic coating, the top surface of the metal now experiences a temperature of only 828 degrees Celsius, because most of the heat is insulated by this ceramic coating. Okay, so now with that, I bring there are much more details, much more intricacies to the engineering designs. Every stage is has been researched upon for 30 years before you have the materials ready to be put inside your jet engine, so that human beings can fly over generations through, yeah. But this is only a snippet of what actually happens inside a jet engine from the materials perspective, what nickel superalloys bring to the table, and why are they considered the most suitable materials for jet turbine blades application. So I will end here my talk. So what did we learn today? So we learned that superalloys are the materials of choice for jet turbine sections. This is something that we can take away from today's lecture. They are the Superman of metallic alloys because they are strong and can withstand very, very high temperatures that can make your flights fly faster, higher, and without the material failing. Okay. And finally, the most important thing is that we understood the link between an apple and a jet engine. Okay. All right. With that, I come to the end. So thank you very much. I hope you liked the presentation.
Thank you, dear Professor, for your valuable words. Your words have truly enriched today's session. With that, we now open the floor for the question and answer segment. We invite our audience to share their questions, thoughts, and reflections. This is your chance to engage directly, so please feel free to raise your hands and we will take your queries one by one. Any questions, please? Please raise your hands, the mic will come to you. Any questions? Yes.
Oh, student. Yes, sir.
Namaskar, sir.
Namaskar.
First of all, I would like to thank you to take this point, this topic. Actually, one of our teachers, he is a physical education teacher. वो अक्सर यही पूछते हैं कि ये इतना बड़ा हवाई जहाज हवा में कैसे उड़ता है.
अच्छा.
और हम फिजिक्स पढ़ाते हैं तो हम बर्नौलीज प्रिंसिपल का उसमें बोल देते हैं प्रेशर डिफरेंस से. बट जो आज आपने ये बताया, ये बच्चे हमारी क्लास 11th के हैं. आई एम फ्रॉम KVGNU, टीचर ऑफ फिजिक्स. तो अभी ये जो आपने बताया सुपर एलॉयज, निकल के बारे में बताया और ये एक डेमो करके भी दिखाया, तो थोड़ा सा इसको और एलोबरेट यदि आप कर देंगे कि निकल वाला जो सस्पेंड वहाँ पे रहा और स्टील वाला नीचे आ गया, और ये जो टरबाइन जो आपने हमें शो करी है छोटी सी, तो इसको किस तरह से एरोप्लेन के अंदर ऐड किया जाता है, कहाँ पर, थोड़ा सा इसको एनलार्ज कर करके, जिससे कि थोड़ा क्लैरिटी और आ जाए. सर काफ़ी क्लियर है, इससे पहले के लेक्चर्स में इतना क्लियर नहीं हो पाया. ऑनेस्टली मैं कहूँ, जितना आज पहली बार हमें ये चीज़ें समझ में आई हैं. एज फार एज कंसर्न एरोप्लेन जो राइट ब्रदर्स ने सबसे पहले उड़ाया था, तो क्या उसमें भी यही सब चीजें थी?
नहीं, उसमें नहीं था ये.
तो वो कैसे उड़ा हवा में?
ये बेसिकली मैं I'll give you in very brief what happens is that what you have अच्छा यहाँ पे I'll pull out the image of the engine. ठीक है ना? तो what you have is that these the combustor section and the turbine section, these blades, there are different stages of each section. Turbine का around there are 9 stages और combustor का there are शायद 4 or 5 stages रहता है. ठीक है. तो ये जो stages है शुरू से end तक they are all connected by what do you call a shaft. ठीक है. तो they are actually mounted onto the same shaft.
Yes,
ठीक है. तो सामने आगे आपका compressor blades और पीछे आगे आपका टर्बाइन ब्लेड्स. और उसमें क्या है, अभी आजकल जो न्यू जनरेशन ऑफ एयर इंजिन्स में जो कि रोल्स रॉयस या जीई बनाते हैं, उसमें क्या होता है, एक शाफ्ट की जगह देयर आर 3 शाफ्ट्स, कॉन्सेंट्रिक शाफ्ट्स. तो दे कैन रोटेट, one can rotate in one sense, the other can rotate in the opposite sense, again the inner one can rotate in the other sense, so clockwise, anti-clockwise, clockwise. So उसमें भी क्या है, these days जी की जेनेक्स इंजन अगर आप देखेंगे या फिर रोल्स रॉयस के ट्रेंड 1000 इंजन अगर देखेंगे तो उसमें क्या है, ये अभी गियर्स भी अटैच कर दिए हैं, ठीक है। तो अगर एक स्पिंडल घूम रहा है तो कंप्रेसर और टरबाइन का वेलोसिटी आपका सेम रहता है।
अच्छा।
और आप अलग अलग स्टेजेस के, बिकॉज दिस कॉन्सेंट्रिक शाफ्ट्स भी आ गया है, with the advent of concentric shafts, what you can do, you can make these spin at different velocities too. तो यही है मेन चीज आपका। तो रफली तो बेसिकली क्या होता है आपका जो ये जो डिस्क मैंने दिखाया, दिस इज अगेन माउंटेड ऑन दैट शाफ्ट, और डिस्क के एंड में ऐसे ग्रूव्स कटे हुए रहते हैं, ठीक है। तो ये और ये ब्लेड्स जो है दे स्लॉट इनटू दोज ग्रूव्स, ठीक है। तो इसीलिए यू कैन, एंड ईच ऑफ दीज ब्लेड्स वुड हैव अराउंड, इफ आई एम नॉट रॉन्ग, 50 to 60 डिपेंडिंग ऑन द काइंड ऑफ engines that are manufactured.
ओके,
ठीक है। तो अराउंड 50 to 60 ब्लेड्स गो इन onto each of these discs.
ओके, थैंक यू
तो
सो
ये है
मच
roughly, आपको मैं बता दिया जी।
थैंक यू।
So I want you to elaborate on the topic that how we progress through grain boundary and longitudinal boundary in the blades manufactured. The grain boundary system. The grain boundary system. Like
Grain boundary.
How the grain boundary and progress through
Very
longitudinal.
good question. Have you learnt about casting in school?
Yes, yes, yes.
So when you cast, you typically would get these sort of, have you learned about dendrites in casting? That you form
No,
dendrites?
Sir. No, sir.
So what you do is that when you cast these blades, earlier what used to happen is that they would form these sort of crystals, which is very natural
Yes,
to form. Okay. So what you will have, that you will have this mold inside the furnace, then you pour liquid metal, and when you take it out,
Yes, sir.
when you take it out, it cools down, obviously, and when
Yes,
it cools down into this sort of shape and form, which you cannot avoid. Okay.
Yes,
So there
sir.
are these, you will have a lot of rounded grains, lot of equiax grains, and many boundaries. Okay. But now they realize that these grain boundaries are points of weaknesses. So I need to get rid of at least some of the cross boundaries.
Yes.
Okay. What I can do is that I can keep the longitudinal boundaries, because yahan pe jo when they're rotating, the centrifugal force is acting along the longitudinal direction, along the length of the blade.
Yes, sir.
So there won't be, so if they are all aligned properly,
Yes, sir.
they won't fail, because there is no compressive tearing stress
Yes,
in
sir.
transverse direction. So yahan kya kiya, so they still had the mold inside. In order to transition from this sort of a structure to that structure,
Yes, sir.
columnar structure, they started pulling the mold out, but at a very, 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 very low speed.
Yes, sir.
Of the order of a few millimeter, 1 or 2 millimeter an hour. Agar aise karke very slowly, if you pull it down, you would get this sort of a structure.
Yes, sir.
Okay? And then comes the single crystal, for which you need a grain selector.
Yes.
Okay, something. So this is
Sir.
very advanced. This is very advanced grain selector. Grain selector se kya hota hai? You are pulling it down and so you get a lot of these different colored grains. Yeah. But out of these, only one will, in this case, the yellow grain will grow up. Okay. So there is something called the pigtail.
Yes.
Pigtail geometry. So you can go back and search. Okay. So this pigtail is basically called the grain selector.
Yes.
So only one grain, then in this case, the yellow grain is allowed to grow through that pigtail. Pigtail matlab, pig ka tail kaisa hota hai? Aisa hota hai, round. You have seen a pigtail?
Yes, yes.
So this type of spiral structure is there at the bottom, and that allows only a single grain to grow up to the length of the blade.
Yes.
Okay. You go and have a look. There are a lot of literature which is available on the internet now that you have internet. You can read up books. You'll look up for grain selector and directional solidification. Okay.
सर मेरा सवाल ये था कि प्लेन्स में निकल सुपर अलॉय कब से यूज किया जा रहा है, और जब ये नहीं बने थे तब क्या यूज करते थे?
नहीं, ये शुरू से ही आपका निकल सुपर अलॉय ही यूज किए जाते हैं. I'll see if I got a slide. So all of these are nickel super alloys. Yeah, so right from 1960s on, so these are different alloys. So these are different alloys. They're wrought alloys, conventionally cast alloys. Yeah, conventionally cast alloys are the ones which give me the equiax structure. Okay, the conventionally cast. Then came DS cast alloys. Yeah, And then came the single crystal cast alloys. Okay, so over generations, with considerable amount of research funding and research done on these materials, we came to know that the single crystal, we came to have an idea as to how these single crystal alloys can be used. Okay, so since the very beginning, it has been nickel superalloys. Zinc, there is no zinc. Huh? So like zinc, yeah. Aluminium will form a passive layer of alumina. Yes. Yes. Thank you. You asked the question, you answered for yourself. Now, because यहाँ पे देखो, the reason why I say that this is more oxidation resistant because this has got aluminium. Ni3Al has aluminium as opposed to Ni3Al has aluminium as opposed to pure nickel. So that means this will be more prone to, this will be able to provide better oxidation resistance by formation of this alumina scale. And it's actually this alumina scale which forms a very protective oxide on top of these blades and keeps and protects the inner structure of the material. Okay.
Good morning, sir. Sir, my question is that if there are different altitudes.
Oh, okay. Hi. Good morning. Good morning.
Good morning, sir. So my question is that for long flights, there are different altitudes always changing. The temperature is always changing, the pressure. So how does it affect the flow of air in the turbine or anything that functioning of the turbine? Does it affect it?
It does not change the function of the aircraft engine. The temperature might be different, but how different will it be? -50, say it might be -60, or -30. No, you can say that. I'll frame a better question for you. The question can be that sometimes it can fly through places of like Iceland, where you have a lot of volcanic ash formation because of the ejaculation of the volcanoes. You have a lot of these volcanic ashes that fly around. So that is actually a big challenge for the these turbine engines, because what they do is that they go and get deposited on the surface of the blades. Okay, and that sort of tends to stall the rotation of the blades. But little changes here and there does not really matter to the engine operations.
Okay, thank you, sir.
And I can tell you that even if one engine suddenly stops performing, one engine, is however scary it might sound, if you have 4 engines, out of the 4 engines, if one of the engine completely stops performing, you can still complete a 2 or 3 hour flight duration. Okay, so that's why you have 4 engines for long haul flights.
Sir, here.
Yeah, hi.
Sir, my question is with tech, which material can we use in aviation industry, which we are not able to use till now because of manufacturing scalability?
Very good question. So whatever I have shown has been a fruit of long years of research. Okay, so the fact that you are using nickel superalloys, we are using titanium alloys, has come into being after a long period of research in the labs, in the companies. Then they always have to fabricate them. After the end of research, they will have to fabricate, they will have to manufacture the components in large scale, and they have to test them. And then if it fails, they have to again go back to the drawing board. So it's basically a feedback loop that has been working over generations to come up to these sort of compositions, these sort of alloys that we are actually flying. Okay, but the research does not stop here. Recently, in place of some of GE engines, General Electric engines. Where is my, I hate to go back and forth, but yeah, some of the early stages, some of the back stages of turbine sections, which are typically run by nickel superalloys, the back stages here, yeah, which is quite colder compared to the front stages of a turbine section. So they have been replaced by Ti3Al, titanium 3 aluminum, titanium aluminides, yeah, because they're lighter, and if they're lighter, you'll have the engine, you'll be basically flying a lighter weight, and because if you'll be flying lighter weight, you'll be using less fuel. Okay, so there has been a constant drive like this to discover new materials which will be lighter, which will be able to be manufactured in large scale, which will be able to give us the requisite amount of mechanical properties, oxidation properties, good combination of properties comparable to nickel-based superalloys, if not better. So those sort of research is continuously going on the background. So that is what I do on a day-to-day basis in the lab. Yeah. So then, obviously, after you have come up with the composition, if you think that this alloy at a lab scale is giving me much better properties, yeah, then I will go to some company asking them to manufacture this material, this alloy for me. Then I might see that manufacturing is a problem. So these are the things these are the ways how industry and academia can work hand in hand, and has been working hand in hand in development of technologies like this.
Sir, actually, I read about carbon fiber reinforced polymer. Why are they not widely used?
Carbon fiber reinforced polymers cannot be used. No, actually, carbon fiber polymers can be used. This is actually a potential material like SiC with carbon fiber reinforced in silicon carbide. Okay, so there will be, the matrix will be silicon carbide. You know what composites are. You know what composites are, right?
Yes, sir,
so the matrix would be silicon carbide, and your fiber phase will be carbon fibers. Yeah. So your reinforcement phase will be carbon fibers. So those sort of materials are currently being tested, and you can see that. And obviously, you know that carbon is the lightest material of all. So obviously, when you fabricate a blade made of carbon fiber, this will weigh much less and will be able to withstand much higher temperature, because carbon won't be oxidized. Carbon won't be oxidized like metals. But then making into a piece like this is very expensive. And it requires very niche. And in India, we do not manufacture carbon fibers. So we have to be reliant on other countries to supply, or other vendors to supply us the carbon for the carbon fibers. So manufacturing still remains a big hindrance to manufacturing blades like this made out of carbon fiber composites.
Thank you so much, sir.
Which school is this? Which school? Which school?
Father Ignal, Vishali.
Hi.
Good morning, sir. Sir, can we use NS superalloy in fighter jet engine, as the temperature is more in fighter jet engine?
What? Can we use nickel superalloys in?
Fighter jet engine.
Yes, of course. They are used in fighter jets. They are used in fighter jets too. So fighter jets as well as civil aircrafts, you are right that in fighter jets, there is an additional operation that happens after the hot air is blown out from the back. There's something which is called afterburner. Yeah, afterburner. That's why you see the flames coming out. When you look up at the sky, when a civil aircraft is flying, you won't see fire coming out from the back. That would be scary. What would you see? If it flies too high, you would see a trail of white cloud left behind in its wake. Yeah, that is condensate. That is because of condensation. Yeah, but in jet aircrafts, you routinely see fire coming up from the back, and you are still not alarmed. Yeah, because that happens because of afterburning of the air that comes from the back of this turbine section. So that gives you additional thrust. But material-wise, it's still the nickel superalloys and titanium, and the same alloys that are used for civil aircrafts.
And can we use that in rockets?
What?
Can we use NS superalloys in rockets?
Rocket engines are completely different. They're cryogenic engines. They don't work on this principle. I'm not going into that.
Okay, sir. Thank you.
Good morning, sir. My doubt is that why jet engines are not effective at lower speeds while the internal combustion engines are.
कहाँ है आप? अच्छा, वहाँ पे है. Maybe your student.
Students will request you to maintain the decorum because, like, I know you are all excited to have your questions, but at the same time, it is important to maintain the decorum. We'll take one more question, and then because of the paucity of time, we have other things also. Thank you so much.
Sir, my question was why
आप करेंगे? उनको कर लेंगे, फिर आप करिए. बोलिए.
why jet engines are not that effective at lower speeds while the internal combustion engines or radial engines are.
What is the question? What is the question? Can you repeat? एक बार बता दीजिए आप.
Why jet engines are not that effective at lower speeds while the radial or internal combustion engines are.
Why are they? Okay. Not able to follow the question. Something related to internal combustion engine. But what is the question?
Internal combustion engines are effective at lower speeds while the jet engines aren't. Why?
At lower speeds. Why do you want lower speeds? You want to have high speeds, है ना? And jet engine is a type of internal combustion engine. Like internal combustion engine, your turbine entry the efficiency of your engine depends on your ratio of temperature. If you remember the entry temperature to your exit temperature, so that also so the efficiency of jet engine also depends on the turbine entry temperature. Okay, so our drive is to develop engines, develop materials to achieve higher velocity, higher speeds, and higher speeds would mean a higher efficiency, would mean a higher entry temperature of the turbine. So the hotter the air that enters into the turbine section, the better it is, the better will be the efficiency of the engine. हाँ जी, आप पूछें. Yes. अच्छा बताइए, आपको क्वेश्चन पूछने नहीं दे रहे हैं, सर को नहीं पूछने दे रहे हैं. Yes, because they will break. You know, ceramic, which is more brittle, metals or ceramic? Which is more brittle? So they will break. They will be able to withstand higher temperatures, but they will break. They will crack and break. Yes, sir. आपका बोलिए. How? बताइए. मैडम, सर को पूछने दीजिए. Yes. Yes. 1300 degrees. Yes. 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 200 cooling plus coating. No, in that case, it does not. It does not, because the temperature, because if you look carefully at this slide, you would see that the temperature that is experienced by the outer surface of the foil is only 828 degrees, 850 degrees. At that temperature, superalloys, they are operating at almost their peak strength. So this is the reason at high temperature they're able to get stronger. Yeah. Could be, but it does not. In my understanding, there is no softening. Yeah. The moment any softening comes, that will create alarming situation. So, but at 800 degrees, 900 degrees, this is a window. And this curve, the nature of this curve also varies with the composition of the superalloy. There are different grades and composition based on the composition of nickel superalloys. Okay, so you can add a few particular elements to it to make it even stronger. Okay, so if you anticipate that the temperature might be a little higher, so you add the elements like molybdenum, hafnium in a little higher quantity. Okay.
Sir,
मैम पूछ रही
Do they have any?
मैम पूछ रही हैं
Nah, so that's why we want to reduce the weight of the engine as much as possible. Huh? No, lift is different. Nah, this is only during cruising. Only cruising.
Sir, good morning, sir. My question is, what are the challenges faced by the aircraft industries over the period of the time in using nickel superalloys?
So the challenges that we want to fly higher, we want to have a better fuel efficiency, we want to reduce carbon footprints when you fly during your summer holidays. You want to leave behind as little carbon footprint as you can. So how can you reduce the carbon footprint is that you can either use less amount of fuel, yeah. So you burn less fuel, or in other words, you have to make the engine more efficient, yeah. The other thing is that you can, what I was saying is, yes, so you can introduce electrical propulsion besides mechanical propulsion in your engine design, yeah, so that your fan blades are run by electromagnetic forces, yeah, so that you permanent magnets, electricity partly to run the engine, yeah. So these days there are a lot of small aircrafts which use the concept of hybrid propulsion. So hybrid propulsion means part of the engine it's like your hybrid car. Part of it is fuel-driven mechanical system, and part of it is electrical-driven. Okay. So we have the aircraft industries. They are also trying to, or engine industries per se, they are also trying to move more towards electrical propulsion. 100% electrical is not possible except for the small VTOL, vertical takeoff and lift-off aircrafts, very small, or drones, or very, very, very light aircraft. For medium-sized, there are manufacturers which are coming up with design of hybrid engines. Yeah. Yes.
Sir.
Students, sir, would be there with us for a couple of minutes once the complete program gets ended.
इनका कर लेते हैं.
I would request you.
इनका कर
Okay, we'll take this question and then I'll request the students to ask your questions once the session gets over. Thank you so much.
ISRO and DRDO. वो सेम एलॉयज यूज करते हैं. सेम निकल सुपर एलॉयज यूज करते हैं. नहीं. Maybe the design of the blades will be different. Maybe the blades will be thicker in cross section. Maybe as I say, the design might be different. But that is basically has to do completely with engine design, nothing to do with materials. So in terms of materials, they all are the same. They have to use the same grade of alloys that are available. Okay. Or unfortunate thing, let me tell you the unfortunate thing. Unfortunate thing is these sort of blades, the one that you just saw, these sort of blades, single crystal nickel superalloy blades, are not manufactured in India. Okay. So this is a challenge, as the gentleman there was asking. This is material-wise, this is also a challenge. So we need to learn, we need to come up with our own technologies to manufacture these blades in-house. Okay. All of these are imported. And imagine importing thousands of blades every year for aircraft. How expensive would that be? Thank you.
It is truly an honor and a privilege to stand here today to express our deepest gratitude to Professor Ayan Bhowmik for taking time out of his busy schedule to be with us and to share his valuable insights with our students. Your lecture today was not just informative, but truly inspiring. Your words of wisdom have enlightened every one of us. Can we capture the moment with a group photograph? Sir, please, you have to stand here.
No. With whom? Oh, अच्छा ऐसे ऐसे कर ये भी आए है ना ये भी इसको भी आने दीजिए
Thank you, sir. As a small token of our appreciation and respect, we would now like to present you with a memento. This is not just a symbol of today's event, but our heartfelt thanks to you for your generous contribution to our academic community. May I now request Professor Anikesh Jain, the faculty coordinator for the series, to do the honors. Sir, please. Thank you, Professor Ayan Bhowmik, sir. Thank you, Professor Anikesh Jain, sir. Now, I'll request Professor Anikesh Jain, sir, to furnish you all with some beautiful words, inspiring words. Thank you.
Hello, everyone. I think it was a wonderful session. And you must have now understood that though an idea gets conceptualized in brain, and maybe you test it in laboratory, but the real validation of it happens when it is finally validated in field where the harsh condition, the variation, and among all scenario, it has to prove its, you can say the mental, or basically it has to be verified. In fact, many of you might have gone inside an aircraft, and you must have noticed that the engine produces a lot of sound, right? The engine is very noisy. But the moment you are inside the aircraft, you can talk peacefully, right? Outside it is so noisy, and inside the aircraft, you don't feel it. So how does this happen? Like actually inside the aircraft also there is a lot of electronics. You produce a sound which kind of cancel the sound which is getting produced outside, right? So there are a lot of noise cancellation circuitry which has to be put inside the aircraft so that even though in a noisy environment, you can feel perfect calm, right? So you see like a lot of things happens which we may not notice, which we may not feel, but these things are there. And the important lesson from the today's lecture is whatever is designed, it has to work under all condition. And in fact, sometimes you design it for a scenario which may not be even practical, but just to extend the range so that if such situation arrives, for example, think about tires of the aircraft. You know, these tire, even if temperature goes 400 degrees Celsius, 500 degrees Celsius, they will not burn because the material which is used, it is used in such a way so that it can withstand those temperature, while the normal tire will easily burn at that temperature, right? So it depends what you are designing for. You have to understand it, and you have to make sure that things doesn't fail. And that is the reason we are even going into the space where we are even not sure about the conditions, right? Still, we are able to fly things there because we are designing it for those conditions which are not even practical on Earth, but we are just extending so that things should keep on working. But this is a continuous lesson, and I am pretty sure many of you will take this journey and continue this journey where you yourself will be developing these things, and tomorrow we will be there to just witness it, what you have actually developed. Thank you, guys.